All right, in this lecture, we're going to spend a bit of time talking about the very important factor of the size of a hash table. We've talked a little bit about this before. We'll flesh it out quite a bit more today. The question is, how does the size of the table, the overall size of the table, affect the runtime of the hash table? And as a reminder, we have this definition of the load factor, which we call lambda, which is just the number of items stored in the hash table divided by the size of the hash table. And so we're thinking about how does that denominator affect the runtime, and how does it affect the number of collisions that we're going to get? If our table size is large, then the denominator in that equation or that fraction is large, so we're going to have a smaller lambda. And as a result of having a smaller lambda, we're going to tend to have fewer collisions because there are more available slots for everything that we stored in the table if the number of items is constant. And as a result, we're going to have a faster running time. And we hope that if the table size is large enough, lambda is small enough, we'll get close to constant time per operation, whether that operation is insert, query, or remove. But if the table size gets small, that's going to increase lambda, and we're definitely going to get more collisions. And I should say that the reason I wrote probably here is that we're going to get more or fewer collisions depending not only on the table size, but also on the hash function itself. But if we reduce the table size, then we're definitely going to get more collisions because of the pigeonhole principle that we've talked about before. And as lambda goes up, because of a smaller table size, we're going to get a slower running time because we're definitely going to get more collisions. And this can be as bad as linear time per operation, where n here is the number of things that we've stored in the table. And if you think about, imagine a linear probing hash table where you have filled the entire table except for one slot, then searching for that empty slot to insert one more item, which would completely fill the table, would require order n to search the entire table in many cases, unless you got really lucky. And as we'll see later in today's discussion, if the table is too small, then even if there are many empty slots, sometimes open addressing cannot even find those slots. But we'll talk more about that later. The next major thing that we need to talk about is prime table sizes. It's really best to use prime numbers when you're choosing the size of your hash table. For example, prime numbers like 11 or 23, 37, and so on. And the reason for this is it maximizes the chance that we will find an empty slot when we're probing the table, especially when we're using open addressing and we're using search patterns that step by different amounts or different stride lengths. Okay, so we want to use prime table sizes, but imagine that we didn't. Imagine that instead we used a table size of 12, which is not a prime number, obviously, versus a prime number like 11. Well, if 12 being a composite number, if we use that as a table size, imagine then that we were doing double hashing. With double hashing, if we get a collision, we stride through the table looking for an empty spot by using a step size that is exactly the second hash function modulus the table size. Okay, so whatever that second hash function returns, modulus the table size, we're going to step by that amount. And that amount could be anything from 0 up to table size minus 1. Well, the 12 being composite has the following factors, 2, 3, 4, 6, and 12. And if the second hash function returns any of those factors or a multiple of any of those factors, we will not be able to search the entire table. Okay, so if the second hash function, for example, returned 2, and we started at 0, we would probe 0, 2, 4, 6, 8, 10, and then back to 0, 2, 4, 6, 8, 10, and so on. And we would repeat this. In other words, we would not probe any of the odd slots. Similarly, if we probed with 3, then we would probe 0, 3, 6, 9, 0, 3, 6, 9, and so on. Again, this is because 12 has factors of 2 and 3, but it's not just 2, and 3, right, it's any multiple of those, which includes 4, 6, and 12 itself, as well as anything larger than that. Okay, so a composite number is a really bad idea for most hash tables. We want to use prime numbers. If the table size was 11, it has no factors other than 11. So the only times when we might have a problem where we would repeatedly probe some entries without looking at others is if we return the second hash function returns 11 itself or some multiple of 11. So it's much less likely that we would that the second hash function in double hashing would cause us such a problem. And just to prove the idea, if we started with, say, 2, a stride length of 2, we would go, if the table size is 11, we would probe 0, 2, 4, 6, 8, 10, and then we would go to 12, but 12 mod 11 is 1, and then we would go to 3, 5, 7, 9, and at this point we've probed every slot in the table. Okay, so, and that would be the same if we used 3, 0, 3, 6, 9, and then 12 goes to 1, 12 mod 11 goes to 1, and then 4, 7, 10, and then 13 goes to 2, 5, 8, and then back to 0. So again, we've probed every slot in the table, right? So, and this is true for any number that is not a multiple of 11. So prime numbers really give us this benefit that we will be able to probe through the entire table because the table size is prime. So the takeaway is that prime table sizes distribute hashes more evenly than non-prime sizes or composite sizes because prime numbers are just not as likely to have common factors with the hash values that we're using to walk around the table or to place items in the table. So use prime numbers. We'll come back to and touch on which prime numbers to use in a few minutes. Now we want to look in particular at quadratic probing because there are some interesting interactions with quadratic probing that you need to be aware of. It turns out that even if you use a prime table size, it's possible for quadratic probing to run into an issue where it cannot find an empty slot even when many of them are available. So in other words, quadratic probing can run into the problem where there are many empty slots, but the probing pattern, even with a prime table size, cannot find any of them. So let's do an example. Let's imagine that we have a table size of 7, which is prime, which is good. And then we probe starting from index 0. We would probe I equals 0, I equals 1, I equals 2, I equals 3, and those would be squared. So our probing pattern would be 0, 1, 4, 9, 16, 25, 36, 49, 64, and so on. But if we take all those numbers and compute them modulus 7 to look at where they actually probe to in the table, notice that the 0th probe, or the first probe, would go to slot 0, which we could use. And then the I equals 1 probe, 1 squared is 1, and we could use that. I equals 2 would go to 4. I equals 3 would go to 9, which modulus 7 would be slot 2. So far, we've been able to use slots 0, 1, 4, and 2 without having any problems. But as we proceed, when I equals 4, 4 squared is 16, which leads us to slot 2, which has already been probed. We can't use it. I equals 5 leads us to 25. 5 squared is 25, which leads us to slot 4, modulus 7, which we can't use because we've already probed it, and so on. 36 leads to 1, which we've already seen. 49 goes to 0, which we've already used. 64 goes to 2, which we've already used, and so on. Okay, so notice we've only been able to fill 4 out of the 7 slots. There are still 3 slots that are empty. In particular, slots 3, 5, and 6 have not been touched, but we were not able to probe them starting at index 0. Okay, And that's with a prime table size. We know that if you don't use a prime table size, if you use a composite table size, it could be worse. And in fact, that's the case. There are cases that I could show you where if you don't use a prime table size, you can only probe a quarter of the slots in your table. And so that's even worse. So you do want to use a prime table size, but you still, when you're using quadratic probing, uh, you want to make sure that your load factor is less than 1/2 at all times. So in other words, the table should only be at most half full. Then you are guaranteed that you should be able to find a spot that's empty. And in order to prove this, we would have to do a proof, which I'm not presenting here. Um, and I will reiterate that a prime table size is a good idea regardless of which probing strategy we're using. Okay, the last topic for today is the topic of rehashing. Rehashing is what we do whenever we need to increase the size of our table because we're running out of space in our table. When the lambda gets too high, we should reduce lambda. And the reason we reduce lambda is, of course, so that we can maintain a fast running speed, because the lower that lambda is, the faster our hash table is expected to run. And in the case of quadratic probing, as we just saw, we want to keep lambda at most 1/2 or less than 1/2, because if it's not, then we won't even be able to find an empty slot in some cases. And the way that we decrease lambda is to increase the table size. And the one thing to be aware of here is that in order to resize the table, we can't simply create the new table and copy the items directly from the old table to the new table in the same positions. They have to be placed in new positions because their order changes, because the place where the index where we position them depends entirely upon the modulus, and the modulus is the table size itself. The table size is changing, so the modulus is changing, so the positions of all the items in the table are changing. So here's some pseudocode for doing this. First thing to do is, of course, allocate a new or bigger table. And then we would look at all the entries in the old table. And if it's active, then insert that item into the new table. And that insertion, that is the rehashing step. So we have to compute the hash on that item with respect to the new table size and then place it wherever it belongs in the new table. And of course, this is a costly operation. It's going to be at least order n time. Notice that it could be significantly more if the table is fairly large but empty already, because we have to loop over everything in the table, not just the active items in the table, but all the items in the table, including empty and deleted ones. And it's worth pointing out that when we do this, we are clearing out the deleted items. We don't reinsert the deleted items into the new table. And so that means that anything that was deleted now becomes empty. And that makes it more likely that if the load factor was high because of a lot of deleted spots, the load factor will go down even further because we'll have more empty spots available. When we create this new table, how big should it be? Well, it should be a prime number, of course, and a good rule of thumb is when we're reallocating a data structure, we make it that's based on an array, we reallocate to at least half as big, or at least twice as big as the old table. And so you need a prime number that's at least twice as big as your old prime number. Well, this sounds like you might need to add some functions in your hash table which can calculate prime numbers on the fly. But if you think about it, you could pre-compute a list of prime numbers that are at least twice as big as their predecessors. So for example, if you started with the prime number of 31, the next prime number that's at least twice as big as 31 is 67, and then proceed to 137, 277, 557, and so on. And then you could get up to 500, what is this? 587,742,049. So with this list, I've made it so that only 25 numbers in this list, including all the numbers that I skipped over with the ... there are only 25 numbers in this list, I could store those in my code, and then I have all the prime numbers I would need for storing up to half a billion or more than half a billion things in my table. Okay, so we can just pre-compute these prime numbers. All right, that's it for discussing the sizes of tables. Next lecture, we'll talk a little bit more about odds and ends, about different types of hash tables.